Let's talk a bit about how precise our measurements are and how we describe that using this idea of uncertainty. So when we are taking measurements, there's going to be two types of uncertainty that we run into in physics. Systematic and random. So systematic is due to the tool or how the tool is used. Or unaccounted variables. So these are things like my ruler only measures to the nearest centimeter, or the room was warmer than we expected and it caused the temperature to be higher than was ideal. Or if you were like the meter sticks we have in the classroom have a little like bit on the end of them that the measurements don't go to the very end. So if you just measure by sticking the meter stick up against a wall and measure, the tool was used kind of improperly in that case. So you're going to get a systematic error. So these should skew your results in a defined way. They'll either make your number too big or too small. Random are due to the inherent randomness of measurements or the universe, basically. So this is not like, oh, I couldn't do it right. This is when you take multiple measurements, you're going to get different results, especially if you're going to a certain level of precision because of the way that tools work. There's going to be an inherent randomness when you do trials over and over again, or when you take measurements over and over again, even if you're measuring the same thing. So these are the two types of uncertainty that we're going to deal with. We're going to ultimately lump them all together, but I want you to be aware that there are two different types. How do we estimate this uncertainty? Again, we're going to be lumping kind of things together, but when we have the uncertainty of a tool, if it's an analog tool, so say a meter stick that's got markings on it, or a clock that you're looking where you're watching the second hand go by, the uncertainty is half of the smallest marked increment. So if these are centimeters, so 1 centimeter, 2 centimeters, 3 centimeters, and I use this ruler to measure something, my uncertainty is plus or minus 0.5 centimeters, because my smallest increment is 1 centimeter, so my uncertainty is plus or minus 0.5. There might be places where you estimate a larger uncertainty, like if, for example, something was vibrating or shaking, and you're less confident in the value, then you might choose to use a larger uncertainty than this. For digital, the uncertainty is likewise half of the smallest place value. So if it reports 0.0010, that would be plus or minus 0.00005, because this is the smallest marked increment. So half of that, half of basically 0.0001 would be 0.00005. Likewise, if you're using a digital scale and you're seeing that the number is fluctuating, then you might choose, okay, I'm only going to take these first two digits because these last two digits are changing rapidly. So I'm only going to write down these first two, so my uncertainty would be 0.005. So now, when we're talking about uncertainty, there's an important idea known as relative uncertainty. Because up to this point, we've discussed absolute uncertainty, which is the actual specific defined value. So on the previous slide, 0.05 is the absolute uncertainty. It is the value that is the uncertainty. If we divide by the measurement that we took, then we will find the relative uncertainty. And you can think about it like, what percentage of our measurement are we uncertain about? And that's important because if your uncertainty is 0.5 centimeters, if your measurement was 0.1 centimeter, right, your uncertainty is huge. Your uncertainty is plus or minus 5 times my measurement. But if my measurement is 1 kilometer, plus or minus 0.5 centimeters, that's absolutely tiny. So if you take this 0.5 and then divide by your measurement, either the 0.1 or the 1 kilometer, that will give you what we call the relative uncertainty. And that's going to be really important to use for when we talk about propagating our uncertainty.